And we're going to do a bunch of solving questions to finish out our chapter.
Is there anything after the chapter, or is that just the end of the unit?
This will be the end of the unit. Write it down anyway. It's just easier to take it from your phone. Okay. And while you're writing that down, I'm going to hand out your take-home quiz that's due on Thursday. Can I scroll down to here?
Yeah.
So that you can write down our first example as well. So, here are our strategies. We cannot solve an equation if you have two different trig functions. So one of the strategies is, can you change everything to be the same? And in this case, the answer is no. There's no way I can change cotangent to cos. There's no way I can change cos to cotangent without also including a sine, and then I would still have two things that are different. Okay? Do we have anything in common? Can I factor out a common factor? No, there's nothing in common. But I could change to sine and cos and see what happens from there. So in this example, I could change cotangent to cos theta over sine theta. And then I could multiply to get rid of the fractions. So my fraction, I'm dividing by sine theta. Multiply both sides by sine theta. This side just becomes cos theta. And this side becomes 2 cos theta sine theta. Again, now I go back through my strategies. Can I change it to all the same function? No. I can change sine squared to 1 minus cos squared, but unless it's squared, you can't change it. So you can't change sine to 1 minus cos. But we can factor. So the next thing we'll want to do here is make one side equal to 0. And you had a question just like this on your first take-home quiz. Right? We have a common factor of cos theta that you can pull out, leaving you with 2 sine theta minus 1. That splits it right there, and now your trig functions have been separated, and you can solve for each separately. When is cos theta equal to 0? When theta is pi over 2 and 3 pi over 2. When is sine theta equal to a half? It's your pi over 6 family, quadrant 1, and quadrant 2. Reread the question. What was the domain? Good. From 0 to 2 pi. So I don't have to do a general solution or anything else after this. Okay. Next example. Continuing on page 666, or if you have to go to page 667, that is fine. Things just got more complicated because we got more formulas. At the beginning of this unit, we did multi-revolution questions with a 2 theta or a 2x. But now we have double angle identities, which allow us to change cos 2x to something else. So the question is, when should you think of a question as a multi-revolution question, and when should you think about using your double angle identity? I think this is the meanest thing about math, where you learn something more and it makes something you already knew harder. Because now, it used to be if you saw a 2x, you'd be like, the only thing I know is multi-revolution question, so it has to be one of those. But now, it could also be a double angle identity. And how do we tell the difference? Well, I would solve it as a multi-revolution question if the only thing you have is the cos or sine 2x. And I would use my double angle identity if I have another trig function in the question. All right, if I scroll down to there. So here are two questions that have a 2x in them. The one on the left, I would say is a multi-revolution question, because the only trig function you have is the cos 2x. So how do we solve a multi-revolution question? Well, I would get that cos 2, I would get the cos 2x by itself by adding root 3 over 2 to the other side. And then, how do I solve a multi-revolution question? First of all, I take my domain, multiply everything by 2. So I now know that I'm going twice around the unit circle. I solve for 2x. When is cos equal to root 3 over 2? What family is that? Power 6. In what quadrants? Quadrant 1 and 4. And that's the first time around. The second time around, you would add 2 pi to each of the first ones. And you would get 13 pi over 6 and 23 pi over 6. Then solving for x, divide everything by 2. And we have our solution. The second question on the right has a sine 2x and a sine x. So this one won't be a multi-revolution. Instead, you'll go to your formula sheet and you'll change the sine 2x to 2 sine x cos x. And then use your strategies that we wrote down before. In this case, you have something in common, so make one side equal to 0 by subtracting sine x on both sides, and you have a common factor of sine x. Very similar to the question we did at the beginning. So when is sine equal to 0? 0, pi, and 2 pi. When is cos equal to a half? Pi over 3 family in quadrant 1 and quadrant 4. double check your domain. It includes 0 and 2 pi, so I can keep all of my answers. Is everybody good? Not yet? Let me know when you're done writing this down. We're good? Alright, so now we can go to example 4 in our textbook. So turn back to page 657. And we see that we have a sine 2x. Is this a multi-revolution question, or is this an identity question? It's an identity because we also have the cos squared x. So the first thing we're going to do is we're going to take the sine 2x and use the formula to change it to 2 sine x cos x. Which just, with the half and the 2, this just becomes sine x cos x minus cos squared x equals 0. Do you have a common factor? Yes. You can pull out the cos, leaving you with sine x minus cos x. So if I split it here, this part is solvable, but this part is a little bit different because it still has 2 trig functions. Can you see that this factor, the only way it's equal to 0 is if sine x is equal to cos x. So I can solve this first one, cos x equals 0, because on my pi plate that happens at pi over 2 and 3 pi over 2. But solving sine x equals cos x, there's 2 methods you can do this. One, you can think about your pi plate. Yeah, you just, where are the x coordinate and y coordinate the same? Pi over 4 and 5 pi over 4. Or, the other thing you could do with this equation, sine x equals to cos x, is if you divide both sides by cos, you would get this. And what can you change sine x over cos x to? And then where is tan x equal to 1? At pi over 4 and 5 pi over 4. So, this question is an identity question because we had that other trig function. We need to double check our domain because we just solved it between 0 and 2 pi. Oh, good. Oh, but they didn't include 2 pi? Oh, it doesn't matter. So we're done. Now, we are going to take the last half an hour to practice solving. And I have lots of questions to practice solving. First of all, I'm going to get you to circle 12, 13, 14, and 15 on your textbook questions. And then on the back side of your proof, okay? There's a bunch of them that are circled. You can ignore the circles. Instead, put squares around 8, 9, 11, 12, 14, 15, 21, 27, 29, and 31. So that's on the back of your proofs page, and these ones are your textbook ones. Was this light red the whole time? Nobody said anything. Okay. Grab that one right there.